Today you're going to be talking about the parts of a wave, what makes waves, and if we change one part of a wave, what's going to happen. So the terms that we're going to learn is about wave trains, wavelengths, periods, frequencies, amplitudes, and origins. Again, we're going to repeat a lot like we've already talked about in previous classes and videos, period, frequencies, but we're also going to introduce new terms, wavelength, amplitude, origins, and wave trains. So we're going to look at the anatomy of a wave, how we measure waves, calculating periods and frequency, which we've already done, and what happens when you're adjusting amplitude and wavelengths. So again, going back, simple harmonic motion is when something that has a cyclic thing, it's repeating after each other, is going to have an equilibrium. So a period, again, is a measurement of the time required to complete a full cycle. This is a new word, amplitude. Amplitude is a measurement of the maximum distance the wave has compared to its equilibrium. Now, if it's a pendulum, it's the bob itself. So if a pendulum angle increases, you're increasing that amplitude. In sound, that would be the compaction of those atoms, those air molecules. So the compression versus that rarefaction, how big those are comparatively. Frequency is how often those cycles, how many tick-tocks there are in a given second, or how many of those compression rarefactions in sound waves happens in a given second. Frequency is measured in hertz. Now, we have these equations. We've seen them already previously, but time, t, is actually period. So period is measured in time. Again, it's measured in seconds. So period and t. And it's equal to 1 over f. Frequency is just 1 over t. They are inverse relationships to each other. So if we flip this fraction, we get f. Flip this fraction over, you get 1 over t. So they're just flips of each other. Period is measured in seconds. Frequency is measured in hertz. Now we're going to talk about wavelength. Wavelength is symbolized by the letter lambda. Lambda is the Greek letter L, and it is symbolized with a diagonal line with a kickstand. So try to draw that a couple times in like a little corner of the sheet just to get used to it. Easiest way is a 45-degree angle down and then add a little kickstand. Lambda stands for the wavelength. That is the length of each wave. The crests are the highest points in the wave. The troughs are the lowest points in a wave. And the wavelengths a wavelength can be also described as distance from crest to crest or trough to trough. Amplitude, though, is the maximum distance a wave travels from its equilibrium position or the origin. So let's go through these and kind of discuss them out. So first we have crests. These are your crests. They're the top of your waves, and your troughs are the bottom of your waves. Your equilibrium and your origin is that middle point. So you can think of this as a pendulum moving back and forth over time. That pendulum is moving up back and forth, and here's its lowest point, here's its highest point, and if it stops, it's going to stop right here. Sound would be the same way. Here's where its highest compression, here's its rarefaction, and here's that just normal, silent, no sound at all is happening right here. Now, amplitude is the height of the wave from the highest point to the origin. The wave train is the whole length of the waves, all these waves. And it's basically it's as if you took little bits of these waves, attached them together like a train, cars, and made a full train. That leads us to the wavelength. The wavelength is from crest to crest, trough to trough, or from one point of the origin to another point, repeating. It is not from here to here. That's a common misconception. This point to this point is actually a half a wavelength. And how you can tell is this wave, if it's traveling to the right, is going up. Now it's going down. You need to go to a point where it's repeating again, going up, crossing the origin. So this point right here, from this point crossing the origin to this point crossing the origin is your wavelength. You can tell because it should be the same distance as that. So if you put your fingers on the screen and measure out that distance and put it right here, that would be the wavelength. And it should be the same here. So what you can do is do this demonstration, and it will really help you understand nodes and versus antinodes. Take a rope of some kind, tie it to a doorknob, or have somebody hold it in your hand. It could be a rope, it could be a slinky, it could be a piece of string, it really doesn't matter. And you're going to kind of flick your wrist up and down, and what's going to happen is you're going to get to a point where if you flick it just fast enough, just right, you're going to get to this point where there's going to be points where they don't move. There's going to be positions where they don't move back and forth. Those points that do not move and they keep repeating, so it would be right here and right here in this picture, where this point will go up, down, this will go down, up, and that up, down, and these points that don't move are called your nodes. Nodes mean no movement. Antinodes is where you have your maximum movement. Up, down, up, down, up, down, up, down. So, the time that needs for one wavelength is your period and is measured in seconds. How many wavelengths are in 1 second is your wave's frequency and is measured in hertz. The speed of a wave is going to be your wave's velocity and is measured in meters per second. Now, this is really important. Waves transfer energy, not matter. If you flick your wrist on a slinky and it produces a wave, the atoms themselves do not transfer to the other person. The steel atoms don't move. Energy is moving along that slinky, but not the atoms. When I speak, the energy is leaving my mouth, going to a microphone, which is going to your speaker, and that's going to your ear. The air molecules itself by the speaker are not going to enter into your ear. When you talk to somebody, the air molecules from your mouth and your larynx are not leaving your mouth and entering somebody's ear. It's the energy that's transmitted through the air. Now, waves propagate that energy and they travel through a medium, or aka material. Those properties, depending on what property is, how elastic those are, can change the speed of that sound. So, traditionally speaking, the more dense the material is, the faster the sound is. Now, that is not always 100% true, but that's a good general rule. If you can see, air at 0 degrees is 331. Air at room temperature, 20 degrees Celsius, is about 343. So, something that's a good round numbers to kind of get the speed of sound. That's 740 miles per hour. That is the speed of sound in air. But underwater, on the other hand, it is 1,500 meters per second. And in iron, 4,000, glass, 5,000. This is because the air molecules are more spread out as the air propagates that sound. It kind of spreads out. It has to take longer to hit another air molecule to spread on. Water, they're a little bit denser, closer together. Iron, really, really close. For an example, if you want to try this out, put your head on the table, tap with your one finger, so your ear's on the table, and tap as far away as you can reach without lifting your ear from the table. Tap as very lightly as possible. You will hear it travel through the table, and you won't hear it through the air. So you'll hear it through one ear, but not the other. This is showing you that that sound wave is traveling through the solid material of a table faster than in air. So again, antinodes, maximum motion, nodes where there isn't any motion. Now we're going to go into amplitude. Amplitude is the height of the wave, and again is measured from the origin to that height, and it is also how much energy. So amplitude equals high energy. It's symbolized by the letter A. And if you increase the amplitude of a wave, you're increasing the overall height. Amplitude in sound is related to loudness or volume. So when you turn up the volume on your speakers, on your headsets, when you're listening to your music, you are increasing the amplitude of the sound. You're just increasing the overall heights of the crest and the lows of the troughs. That's what an amplifier does in your car. Wavelengths, on the other hand, is the distance from crest to crest. It's the length of it. Again, symbolized by the Greek letter lambda, which is that you can add that little florals on the bottom and tops if you want. I just do a straight 45 degree with a kickstand. Now, if you stretch it out, that would be like as if you wanted to increase the wavelength, it would be like nailing one end and then pulling this wave to the right. You're going to slowly stretch it out here and really stretch it out here. Notice that the height from here to there is different than the distance from here to there. You stretched out the overall thing. Height, the wavelength, is related to the frequency. And frequency is how often it occurs in one given time. It is measured in hertz, and it's how often something happens. So you got 1, 2, 3. So, you got those back and forths. Comparative to the 1, 2, 3, 4, 5, 6. They're much, much faster. The frequency of how fast that little ball went up and down, that's your frequencies. And so we can actually break it up. We saw that there's 1, 2, 3, 4 full up and downs, tick-tocks in 1 second, comparative to the 10 that happened in the previous one. And you can reverse that and actually count them out, but that's what happened in the same amount of time. Period is again symbolized by the letter T, and period is related to frequency as the inverse. Inverse meaning 1 over whatever you're looking at. So here's a practice. An ocean wave hits the sandy beach every 4 seconds. What is the period and what is the frequency? Well, again, period is the time. It's 4 seconds. What is the frequency? 1 over that. That'd be 0.25. So if you have any further questions, go ahead and ask your teacher. Thank you.